Every year, over 2 billion tons of steel are produced worldwide, but only a fraction of it becomes I-beams, the backbone of skyscrapers and bridges. These factories are entire cities with smokestacks as tall as a 30-story building and cranes that can lift a railcar along with its locomotive. For one beam to be born, ore goes through over 2,700 degrees Fahrenheit in a blast furnace, a dozen rolling stands, and is cut by a disc up to 2 meters in diameter. A modern rolling mill produces a new beam every 30 seconds, like a car assembly line, only each car weighs 3 tons. Why does the H shape save tons of metal and protect buildings from collapse? I'll show you with a simple example. Watch until the end. One invisible flaw of 1 millimeter, and you'll see what breaks even perfect steel. The entire process begins not in the workshop, but deep in the earth, where iron ore is mined. This ore is transported to metallurgical plants, true industrial cities, with smokestacks as tall as a 30-story building. Here, the ore is mixed with coal and melted in blast furnaces at a temperature of over 2,700 degrees Fahrenheit. Such a temperature can melt copper coins in a matter of seconds. As a result, liquid iron is obtained, which is then purified of impurities and turned into steel. Steel is not just iron. It's an alloy to which a precisely calculated amount of carbon and other elements are added. Even 0.1% can drastically change the metal's properties. Too little carbon, and the steel will be as soft as clay. Too much, and it will be as brittle as glass. Therefore, steelworkers operate with the precision of pharmacists, controlling the composition of the melt using computer systems. When the steel is ready, it is poured into huge ladles and transported to the next stage. Here, the molten metal is poured into special molds, resulting in blanks called billets. These billets resemble huge metal bricks weighing up to several tons each. They do not yet look like beams. They are just rectangular bars of hot steel that glow red in the dark. The real magic of transforming billets into I-beams happens on the rolling mills. The steel blanks are heated to high temperatures and then passed through a series of rollers to give them the desired shape, including I-beams. These mills are true monsters of heavy industry. Imagine a machine the size of a trolley bus, consisting of dozens of rollers with a diameter of more than 1 meter. Each roller weighs as much as an average car and spins at the speed of a bicycle wheel. The heated billet passes through a series of rollers that gradually give it the desired beam shape. The rollers exert enormous pressure, giving the beam structural strength. The process resembles rolling out dough, only instead of flour, there's a multi-ton steel blank, and instead of a rolling pin, there are rollers that could flatten a car in a second. In modern steel rolling, I-beams are rolled on universal rolling mills. The web of the I-beam is rolled between the upper and lower horizontal rollers, and the flanges are formed simultaneously between the side of the horizontal roller and a vertical roller. This is like a complex choreography, where dozens of rollers move in sync, gradually transforming the rectangular blank into the elegant shape of an I-beam. Temperature here is critically important. Hot rolling involves passing heated steel through rollers, shaping it while maintaining a plastic working temperature. If the steel is too hot, it might deform incorrectly. If it's too cold, it could crack under the pressure of the rollers. The temperature is controlled by pyrometers, devices that measure heat from a distance, like sniper thermometers. Interestingly, the I-beam shape is not a designer's whim, but the result of precise engineering calculations. Such a design allows for maximum strength with minimum metal weight. Imagine a bridge. The main loads are on the top and bottom of the beam, which is why the wide flanges of the I-beam are located there. And in the middle, where the stress is less, a thin web is sufficient. The rolling process takes several minutes for each beam, but during this time, it passes through 12 or 15 pairs of rollers. Each pair has its own shape, gradually bringing the blank closer to the final profile. It's like sculpture. First rough forms, then more and more details and precision. When the beam emerges from the last pair of rollers, it's still glowing hot, 1,650 degrees Fahrenheit. In the air, it glows with an orange light and can ignite wood on contact. Therefore, the beams are cooled on special racks, where they gradually darken, acquiring the characteristic grayish-blue hue of hot-rolled metal. Hot rolling shapes metal beams at elevated temperatures, making the material more ductile. As a result, this method supports the production of large sections and complex shapes. That is why most structural beams are made by hot rolling. It allows for creating powerful structures for skyscrapers and bridges. But the process doesn't end here. The cooled beams undergo quality control. They are inspected with ultrasound, like conducting an ultrasound on a pregnant woman, only instead of a baby, they are looking for internal cracks in the metal. The dimensional accuracy is also measured with special templates. Even a millimeter deviation can ruin the entire structure of a building. After the red-hot metal has passed through the giant rollers of the rolling mill and been transformed into the recognizable H-shaped profile, the I-beam enters one of the loudest and most spectacular stages of its birth, marking and cutting. Freshly formed, still glowing red or bright orange, the beam slowly moves along a roller table, a long conveyor of rollers. Along this path, it gradually cools, releasing its heat into the workshop air. Gradually, the color of the metal fades, turning to a dark cherry red, and then to the familiar gray. This process, known as normalization, relieves internal stresses in the metal that arose during rolling, and gives the beam the necessary strength and ductility. The beam hardens, turning into a monolithic steel backbone, ready for the next trials. After final cooling, each beam must receive its birth certificate. This process is called marking. A special marking machine, resembling a giant industrial printer, applies a clear and durable imprint on the beam's surface. This is not just a random set of symbols. The marking contains all the key information about the beam. Applying the marking is an act of giving the beam a unique identity. Now, it's not just a piece of metal, but a certified structural element with guaranteed characteristics, ready for use in the most responsible projects. The most spectacular and deafening stage is cutting. Long beams, sometimes over 300 feet, are fed to the cutting complex. The heart of this complex is giant pendulum or circular saws. Imagine a circular saw, but scaled up to incredible sizes. Its blade, reaching up to 2 meters in diameter, glitters with razor-sharp carbide teeth. The process begins with the precise positioning of the beam. The operator, controlling the process from a protected cabin, sets the required length. Powerful hydraulic clamps fix the beam, preventing it from moving even a millimeter. The giant blade begins to spin up, emitting a growing hum that turns into a piercing howl. When it reaches operating speed, the saw is smoothly lowered onto the beam. At the moment of contact, the air shudders from a deafening roar. This is not just a sound, it's a vibration that you feel with your whole body. It's similar to the simultaneous operation of dozens of chainsaws, or the roar of a jet engine at takeoff. This sound carries for kilometers around, announcing the titanic work taking place in the workshop. But the most impressive thing is the speed of the whole process. From the moment the iron ore arrives at the plant to the finished beam takes less than a week. During this time, the metal has time to melt, be purified, solidify, be heated again, and be transformed into a precise structure. A modern rolling mill can produce a beam every 30 seconds. It's like a car assembly line, only each car weighs 3 tons. The finished beams are loaded onto trains by special cranes. Such a crane can lift a railcar along with a locomotive. The beams are transported to construction sites all over the world, where they will become the skeletons of skyscrapers, factories, shopping malls, and bridges. Each such beam is the result of the work of hundreds of people of various professions. Miners who extracted the ore, metallurgists who smelted the steel, rolling mill operators, quality controllers, and crane operators. This is a true industrial art, where the precision of a pharmacist is combined with the power of a volcano. And when you see a new skyscraper or bridge, remember, at its core are thousands of I-beams, each born in the fire and thunder of rolling mills, where the temperature melts metal, and human intellect transforms this metal into the foundation of our civilization. Did you know that over 100 million AK-47 pattern rifles have been produced worldwide since its invention? That's an absolutely staggering number, more than all the service rifles produced by almost every other country combined. This iconic weapon, recognized globally for its ruggedness and reliability, might seem incredibly simple on the outside. But producing these millions of units requires a massive, complex industrial process involving extreme forces, surprising precision, and manufacturing secrets perfected over decades. Get ready to go behind the curtain and see exactly how an AK-47 is manufactured on a colossal industrial scale. The story of the AK-47's manufacture really begins with its design philosophy. Mikhail Kalashnikov intended it to be simple, easy to use, reliable in the worst conditions, and crucially, easy and cheap to manufacture in vast numbers. This design genius meant engineers had to figure out how to make complex parts ruggedly and quickly. The key was often using methods that didn't require extreme precision machining on every single component, focusing tight tolerances only where absolutely necessary for function. This is a core secret behind its mass production success. One of the most visually impressive and important manufacturing processes for the AK-47 is billets, stamping. Unlike many other rifles that use heavier, milled receivers, the AK-47 often uses a receiver made from sheet metal. Picture huge rolls of steel sheet being fed into massive, powerful presses. These presses stamp out the receiver's shape in stages, bending, forming, and punching the metal with tons of force. This high-speed stamping process is incredibly efficient, churning out receivers faster and cheaper than almost any other method. It's a core reason millions could be made. While the receiver is often stamped, many critical components that face extreme stress and heat, like the barrel, the bolt carrier, and the bolt itself, are made by forging. This involves heating steel billets, solid blocks of high-strength steel, to incredible temperatures until they're red-hot and malleable. Then, giant forging presses or hammers pound or squeeze these glowing pieces into complex shapes. The force involved is immense, thousands of tons, reshaping the metal's internal grain structure to make the part incredibly strong and durable. This is where raw power meets shaping, creating components tough enough to withstand the explosive forces of firing. Even though simplicity was key, certain areas of the AK-47 require remarkable machining precision for reliable function. The bolt, which locks into the receiver, and the chamber end of the barrel, where the cartridge sits, must meet tight tolerances. These parts are finished on computer numerical control machines that use hardened cutting tools to shape the tough steel with incredible accuracy. While not every surface needs mirror-like precision, the critical interfaces that ensure safe and reliable firing are machined to exact specifications, often measured in thousandths of an inch. Bringing all these parts together involves other vital metalworking processes. Welding is used to join stamped receiver components and attach parts like the gas block to the barrel. Industrial welding robots, or skilled human welders, create strong, reliable joints. Heat treatment is also critical. Components like the bolt and bolt carrier undergo processes like hardening and tempering, heating and cooling cycles that change the steel's properties, making them incredibly resistant to wear and impact, vital for the rifle's legendary durability in harsh conditions. Once all the metal components are fabricated and treated, they often go through finishing. This includes processes like parkerizing, bluing, or applying polymer coatings. These aren't just for looks. They're crucial for protecting the metal from corrosion, especially important for a rifle designed to operate in wet, muddy, or humid environments. Furniture, the stock, handguard, and pistol grip, is often made on separate lines from wood or polymer and then added to the metal assembly. The final stage is Koblau assembly. While many steps are automated, putting together the hundreds of components of an AK-47 often still involves significant human skill on assembly lines. Workers fit parts together, install springs, pins, and levers, turning a pile of components into a functional rifle. Each rifle is inspected visually and functionally as it comes off the line. The true test of an AK-47's manufacturing is its legendary reliability, and this is verified through rigorous quality control and testing. Rifles are subjected to dimensional checks and material tests. Crucially, they undergo proof testing, firing rounds with an intentionally heavier charge than standard to ensure the weapon can safely withstand extreme pressure. Some are even subjected to brutal environmental tests, dunked in mud, buried in sand, submerged in water, and then expected to fire immediately. This extreme testing validates the ruggedness built into the manufacturing process. Producing millions of AK-47s requires vast factory complexes, intricate logistics, and a highly skilled workforce. It's a fascinating intersection of design philosophy, focused on simplicity, and industrial processes capable of achieving rugged reliability on an unprecedented scale. While the rifle itself is often seen as a symbol of conflict, its manufacturing process is undeniably a powerful example of mass production engineering and durability-focused fabrication. So, the next time you see an image of that instantly recognizable silhouette, remember the unseen journey it took. From raw steel and wood, through giant stamping presses, powerful forging hammers, precise machining centers, intense heat treatments, and rigorous testing, it's a product of a massive, impressive industrial process. It's a fascinating look into the power and precision that builds one of the world's most widespread tools. What part of manufacturing an AK-47 surprised you the most? Let us know in the comments. Every year, thousands of miles of new railway tracks get laid down all over the world. But the Japanese, they've turned it into a true art form. Here, rails the length of a football field are born from the molten lava of steel, reaching over 2,700 degrees Fahrenheit. They're joined together to seem absolutely endless, and the concrete track slabs, as thick as 2 footballs, hide the secrets of eternity and speed. So how did the Shinkansen engineers manage to achieve that almost perfect, smooth ride? An average delay of just 36 seconds and speeds of up to 200 miles per hour? Watch till the end, and you'll find out something you'd never have guessed. We're stepping into a massive Japanese steel mill. The atmosphere is thick with heavy air, a mixture of heat, steel, and the deep hum of powerful machinery. In front of us is the main star of the show, a steel-making furnace the size of a 5-story building. It looks like the tongue of a volcano, glowing a dazzling white hot. Inside is a boiling mixture of iron and carbon. Its temperature is over 2,700 degrees Fahrenheit. The molten metal pours out with a roar into special molds, like a bright orange river of lava flowing down a mountain. The workers look absolutely tiny against the backdrop of the huge machines. After the steel is melted in that huge furnace, it gradually starts to cool, turning from a liquid into a solid but still very hot piece of metal. This piece, think of it as a thick, hot bar several feet long, is then fed into a rolling mill. A rolling mill is a gigantic machine, kind of like a huge meat grinder, only instead of a blade, it has heavy steel rollers that press and stretch the metal. The dull roar gets even louder as the machine grabs the red-hot blank. With a sound like a deep groan and the scrape of friction, the hot metal begins to stretch out, like dough for pasta, but not soft, dense and heavy. Gradually, this bar becomes longer, thinner, and more uniform, and eventually, it transforms into a long rail, 320 feet in length. That's like a football field and then some. The surface of a rail like this has to be perfectly smooth, without the slightest ripple. Because if it's even a little bit uneven, the high-speed Shinkansen train won't glide smoothly over it. It'll start hopping at the joints, like a little frog in a swamp. After rolling, the rail is still incredibly hot. Steam rises from it, and you can hear a crackling sound, like when water hits a hot stove. But this is almost its final form. Long, heavy, smooth, ready for inspections, grinding, and its future. Becoming part of the track for one of the fastest trains in the world. To reduce the number of joints, which are potential spots for wear and noise, Japan uses a method of continuous welded rail. That's when several rails are joined into one incredibly long strip, almost 5,000 feet long, making the rail seem endless. Welding rails for high-speed trains like the Shinkansen is a high-precision technological process. The goal is to turn individual rail sections into a single, seamless strip up to almost a mile long. It's this type of connection that lets them avoid the traditional clickety-clack sound when going over joints, reduces wear, and creates that smooth gliding effect. The welding process happens in several stages. Most often, they use thermite welding, a reliable and pretty spectacular technology. 2 rails are placed end to end, so a gap of a few millimeters is left between them. The surfaces of the future joint are thoroughly cleaned of rust, scale, dust, and any other contaminants. It is crucial that the edges of the rails are perfectly even, like knife blades before being joined. Next, a special mold made of a sand mixture or a heat-resistant material is mounted around the joint. It holds the molten metal during the reaction and gives it the required shape. A thermite mixture, a powdered mix of aluminum and iron oxide, is poured into a small container above the joint. When it's ignited, a reaction occurs, during which a temperature of over 4,500 degrees Fahrenheit is released. As a result, molten iron is produced, which flows down and fills the gap between the rails, joining them at a molecular level. The reaction takes several minutes. During this time, you can hear hissing and crackling, and a bright flame rises above the joint. It looks just like a miniature volcanic eruption. After the metal solidifies in 10 minutes, the mold is removed, and the excess metal is trimmed off. The joint is then ground to a perfectly smooth surface, so the train wheel doesn't feel the transition from one piece of rail to another. The finished joint is checked with laser measurements, as well as with ultrasonic sensors that look for any possible microcracks. A rail like this is installed as a single, solid block and has a minimal number of service points, which lowers repair costs and the risk of delays. In a world where every second is precious, Shinkansen engineers discovered the secret to eternity: slab track. Instead of traditional stone ballast that crumbles under the pressure of time, they created monolithic giants out of concrete. These titan-like slabs reach a thickness of 26 inches. That's the height of 2 footballs stacked on top of each other. The Japanese masters came up with a genius solution: encapsulation elements. Imagine a metal cradle that hugs the rail like a mother holding a child. These cradles not only hold the steel guides, but also isolate them from vibrations and electricity. It's like giving the rails superpowers, the stability of Superman and the flexibility of a dancer. The most genius part of the whole system is what you can't see. Between the concrete slabs and the foundation, the Japanese placed resilient layers that act like giant shock absorbers. In tunnels, slab track works true wonders of economy. A lower track height means a smaller tunnel cross-section, which reduces construction costs by a fantastic 30%. Transporting the sleepers to the installation site is done in several ways, depending on the distance and accessibility. Transporting sleepers by road requires special measures to prevent any movement during transit. Transporting sleepers by rail must be carried out according to a loading plan approved by the railway department. For short distances, special trucks with cranes are used. For long routes, railway flat cars are used. Safety during transport is critical. One concrete sleeper must be lifted by 4 workers, which highlights their significant weight, approximately 165 pounds per worker. For mechanized lifting, special grippers and cranes are used to avoid damage to both the sleepers and the workers. At the construction site, the installation process begins with preparing the foundation. For slab track, which is primarily used on the Shinkansen, the sleepers are installed on pre-prepared concrete slabs. Each sleeper is positioned with an accuracy of 1/4 of an inch, since even minimal deviations can cause problems at speeds of 200 miles per hour. The installation is carried out by specialized crews using precision equipment. First, support points are installed every 2 feet, the standard interval for high-speed lines. Each sleeper is attached to the base with special 1-inch diameter anchor bolts, which are driven 6 inches deep into the concrete slab. The process is complicated by the need to integrate with the power supply and signaling systems. The sleepers have special channels for laying cables, as well as insulators to prevent short circuits of the traction currents. Installers must consider the location of all engineering systems, including drainage channels and grounding. The final stage includes installing vibration isolation pads between the sleepers and the foundation. These rubber steel elements significantly reduce the transmission of vibrations from the trains to the surrounding structures. After the installation is complete, the entire section is tested by a special measuring train that moves at speed and records the slightest deviations in the track's geometry. Even with over 120,000 trains running on the line each year, the average delay is just 36 seconds. Over half a century, the speed has increased from 130 miles per hour to 200 miles per hour, and the passenger flow is now 1 million passengers a day. A new line is expected to be operational at a speed of 310 miles per hour, with an estimated travel time between Tokyo and Osaka of 67 minutes. Construction began in 2011, was initially planned to open in 2027, but is now postponed until at least 2034. Every year, billions of dollars are spent worldwide on developing military technologies. But only one aircraft has become a true ghost in the sky, as invisible as death itself. Its creation cost over $23 billion, united more than 40,000 people from 46 states, and even required the construction of a new industrial city. If you found out what is hidden under its black coating, you would never look at aviation the same way again. Does your country participate in the production of components for military aviation? Let us know in the comments. The design of the B-2 Spirit strategic bomber began in 1979, when the Cold War was reaching its peak. It was then that the US Department of Defense initiated the Advanced Technology Bomber program, with the goal of creating a new generation aircraft capable of penetrating the most advanced Soviet air defense systems while remaining invisible to radars and delivering nuclear or conventional weapons over intercontinental distances. Leading American aerospace corporations participated in the competition: Northrop, Boeing, Lockheed, Rockwell. After a lengthy stage of development and testing, in October 1971, the Northrop-Boeing consortium was declared the winner. It was their project that received the designation B-2 and the name Spirit. Unlike previous strategic bombers, the B-2 was built on a unique flying wing design, which provided minimal radar cross-section and significantly better flight technical characteristics. In the mid-1980s, the B-2's design had to be significantly changed. The mission profile was adapted for low-altitude flights with terrain following, which allowed for even more effective penetration of Soviet air defenses. This led to a 2-year delay in the first flight and a $1 billion increase in the program's cost. By 1989, about $23 billion had been spent on the B-2's development, and even specialists from the Massachusetts Institute of Technology were involved in the work, assessing the aircraft's effectiveness under conditions of strict secrecy. The first public showing of the B-2 Spirit took place on November 22, 1988, at Plant 42 in Palmdale, California, which is where it was assembled. The first flight of the B-2 took place on July 17, 1989. Initially, the US Air Force planned to order 132 aircraft, but after the end of the Cold War and the collapse of the USSR, as well as due to the extremely high cost, the series was reduced first to 75 and then to 21 units, including a prototype, 5 pre-production, and 15 production machines. Almost all B-2s received their own names in honor of American states, emphasizing their uniqueness and symbolic significance for the country. Thus, the B-2 Spirit became not only a technological breakthrough, but also a symbol of American military might at the turn of the 20th and 21st centuries. The production of the B-2 Spirit began not with the manufacturing of individual parts, but with the creation of a completely new industrial ecosystem capable of meeting the unique requirements for technology, materials, and assembly precision. The first and most important stage was the organization of the production base and the development of tools that did not exist before. After the design phase was completed, Northrop Grumman, as the prime contractor, invested over $1,200,000 in creating a specialized integrated composites center in Pico Rivera, California. For this, a former Ford auto plant was repurposed, turning it into one of the world's largest composite manufacturing centers. The production of the B-2 required the development of not only new materials, but also special tools, software, testing laboratories, and automated production systems. At this stage, the following were created: unique molds and tooling for forming large composite panels, automated lines for laying carbon fiber, computerized systems for cutting and shaping parts, and autoclaves for heat-treating composites at a temperature of about 350 degrees Fahrenheit and a pressure of 100 psi. The production of the B-2 began with digital modeling. Engineers created three-dimensional CAD models and then directly manufactured production tools from them, bypassing traditional mock-ups. This allowed for achieving unprecedented accuracy. Even microscopic deviations could affect the aircraft's stealth characteristics. In parallel, a complex network of contractors and suppliers was formed. Over 6,000 companies and 40,000 workers from 46 states of the US were involved in manufacturing components. Boeing was responsible for manufacturing the outer wing sections, Vought aircraft, for numerous composite elements, Hughes, for radar systems, and General Electric, for the engines. Only after the creation of this entire infrastructure did the direct manufacturing of parts, their processing, quality control, and subsequent assembly of the aircraft at the main plant in Palmdale, California, begin. Thus, the production of the B-2 Spirit started with large-scale preparation of the production environment, engineering innovations, and the development of new technologies, which made the creation of this unique aircraft possible. After the large-scale preparation of the production base, the creation of unique tools, and the establishment of material supply chains, the direct manufacturing process of the B-2 Spirit began. Events then unfolded in several key stages, each requiring engineering precision and strict coordination among thousands of specialists and hundreds of contractors. Manufacturing of the main fuselage and wing sections. The manufacturing of the main fuselage and wing sections of the B-2 Spirit began with the production of the world's largest composite aviation parts at that time. The central part with the crew cabin was manufactured by Northrop Grumman, while Boeing made the 65-foot-long outer wing sections and the 50-foot-long aft section. The slightest deviations could affect the B-2's radar cross-section. In total, over 10,000 composite components were manufactured for one aircraft, using the latest automation and quality control technologies of that time. The precision assembly of the B-2 Spirit is a true engineering feat that unfolded in huge hangars specially created for this project. The assembly of the main sections took place on massive jigs, special platforms that occupied an area comparable to a football field. Here, hundreds of engineers, assemblers, and quality controllers worked simultaneously, each responsible for their narrow stage. Thanks to three-dimensional CAD modeling, all parts fit together perfectly. During assembly, laser measurement systems were used, which allowed for tracking accuracy down to thousandths of an inch. Even microscopic deviations could disrupt the aerodynamics or reduce the effectiveness of the stealth coating. Every joint seam was checked several times, and after connecting the sections, it was manually sealed with special materials to ensure airtightness and invisibility. The scale of the assembly was impressive. Just the central fuselage section required over 1,000 hours of labor, and the total assembly cycle for one aircraft took more than a year. All stages were accompanied by multi-level quality control, from geometry to electromagnetic compatibility. It was thanks to such attention to detail that the B-2 Spirit became a benchmark of precision and technological excellence in world aviation. After assembling the main structure, the integration of systems began. Electronics, hydraulics, fuel tanks, engines, flight control systems, radar complexes, and so on. Many subsystems had to be redesigned and adapted to the unique requirements of the stealth architecture. For example, placing the engines inside the wing to reduce infrared radiation. One of the most complex stages was the application of a multi-layer radar absorbent coating. The process took place in special hangars with a controlled microclimate. Each layer was applied by hand and then checked for defects that could increase radar cross-section. After completing the assembly and integration of all systems, the aircraft underwent multi-level tests, static and dynamic structural tests, checks of all systems operation, flight tests in various modes, and special radar cross-section tests. Any identified deficiencies were eliminated, and individual nodes could be reworked or even manufactured anew. After all tests were completed, the aircraft was officially handed over to the U.S. Air Force. In parallel, crews were trained, undergoing specialized training on simulators and in real flights. After the production of the B-2 Spirit ended in 2000, these unique aircraft did not become museum exhibits. On the contrary, they remain at the forefront of technological progress thanks to constant improvement. The U.S. Air Force is investing billions of dollars in modernizing each of the existing B-2s to ensure they meet current and future challenges. One of the main areas of modernization is updating the onboard control systems. Outdated analog instruments are gradually being replaced with modern digital interfaces, which increases reliability, convenience for the crew, and allows for the quick integration of new functions. The crew cabin has been equipped with multifunctional displays, and the flight control system has received new software that provides even greater stability and precision in controlling the flying wing. Every year, over 40 billion coins are minted worldwide, but you'll never guess where it all begins. Imagine giant rolls of metal weighing 8,000 pounds, entering a workshop like armored trains. There, something incredible awaits them. Presses that strike with a force of 200 tons, and furnaces that heat up to over 1,200 degrees Fahrenheit. Every strike is a new story in your pocket. But there's one thing they don't show in any documentary film. And if you watch this video until the end, you'll be the first to find out. The whole show begins not with a shine, but with the dull scrape of metal, as huge coils, resembling giant toilet paper rolls, are brought into the workshop. Only this isn't cellulose, it's copper, zinc, nickel, or special alloys. These rolls are called coinage coils, and they look serious. Each coil weighs up to 8,000 pounds and is up to 13 inches wide, depending on the type of coin. The metal strip is slowly unwound, like a giant snake, and fed into a straightener, a system of rollers that removes waves, bends, and misalignments. Because precision is sacred, even a tiny bend of 1/100th of an inch can ruin the subsequent stamping. The strip thickness is up to 0.125 inches, and this thickness is controlled in real time by sensors, lasers, and automation. Everything is precise because otherwise the blanking press would simply fail or start making crooked blanks. Each metal is for its own denomination. Zinc strips with copper plating, for pennies. Copper-nickel alloys, for nickels, dimes, and quarters. Bronze alloys with manganese, for $1 coins, like the Sacagawea or US presidential coins. These rolls are not only heavy, they are also expensive. Every centimeter must be used wisely. Therefore, the metal also undergoes an automatic inspection for dents, cracks, and residual oxides. Defects are rejected immediately, cut off, and the strip moves on, like a well-sharpened knife. Next, it faces a press battle. But already here, in the preparatory stage, the fate of each future coin is shaped. Because if the strip isn't made perfectly, there will be no George Washington, no Abraham Lincoln. There will be scrap metal. After the metal strip is straightened, leveled, and approved, it slowly but surely enters the zone where its main trial awaits, the blanking press. And if you think this is some boring little press, then throw that thought out right now. This machine is a metal beast, a hydraulic monster that pounds the metal so fast that the human eye can't blink between strikes. These presses don't just cut out circles, they slam into the strip at a speed of up to 750 strokes per minute. Bam, 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 bam. It's like a mixer on steroids collided with a military ram. Inside, dozens of high-precision dies, similar to cookie cutters, only this isn't cookie dough. It's copper, zinc, nickel, bronze. And when they come down, perfectly round metal blanks fly out of the strip, which has been heated to a shine. Their diameter is clearly defined. These are the embryos of future money. They are still without portraits, without inscriptions, without shine, dull, matte, sometimes with burrs on the edges, but already with the right size, weight, and character. And now imagine the scale. One press can cut up to 14 blanks every second, or 800 to 1,000 pieces per minute. In a day, millions of circles. And this is just on one line. And there are dozens of such lines in the mint. When the die strikes, a dozen or two circles are cut from the strip with each blow, and the leftover metal, meaning everything between the circles, is instantly rewound, wound onto another coil, and sent for recycling. Nothing is wasted. Here, you know, money is even in the scraps. The blanks fly out onto a conveyor belt, hot, slightly discolored, with a light trace of oil and dust. They are collected in metal boxes, sometimes even poured like grain, straight from a chute. Clink, clink, clink. And this sound is simply hypnotizing. A metal rain of future coins. The air is thick with dust and lubricating vapors, smells of metal and money. Literally. Did you smell it too? So you've seen how circles are cut from dull metal, but that's not all. They are still raw, matte, a bit dirty, with oily marks from the press. They need a real spa day. So the first stage is washing. The circles are loaded into huge vertical drums that resemble washing machines, only the size of a bathtub. Inside, hot water around 140 degrees Fahrenheit with an acid solution and special detergents. The drum spins. The circles bang against each other like a foamy dance of metal balls. Everything is removed. Dust, oil, traces of oxides. The water hisses, steams. After this, drying. The drum tumbles the circles, drying them with hot air so that not a single drop remains on the surface. Wet blanks are death for stamping. Next, a real fire ritual, the annealing furnace. These metal circles race through a long furnace, 12 to 40 feet long, where the temperature reaches a crazy 1,250 degrees Fahrenheit. The metal becomes red hot, but doesn't melt. It softens. It's like warming up the body before hard work, so you don't tear a muscle. After the furnace comes rapid cooling. The circles fall into a bath of cold water, about 50 degrees Fahrenheit. This temperature shock makes the metal stronger and more elastic. Then the circles are coated with a thin layer of graphite lubricant, so that during stamping, the press doesn't stick or scratch the surface. This is the final cycle of drying and preparation. Now they are shiny, flexible, and ready to take on a pressure of 400,000 pounds per square inch during stamping. From washing and baking, the circles are no longer just pieces of metal. They are real contenders for the role of a coin. But all they have now are clean, smooth discs, without faces, letters, or shine. And now it's time to give them character, a soul, and a history. The tool for this is the coining press. A huge steel machine stands like a rock in the hall, with a mechanism capable of pressing with a force of up to 200 tons. It presses so hard that sparks don't fly from it, but the metal on the circle sinters and takes shape with incredible precision. When a circle enters the press, it is clamped between two dies, an upper and a lower one. Each die, like a carved hammer, imprints all the details into the metal. Portraits of presidents, coats of arms, dates, inscriptions, fine lines, and even the smallest letters. All this is incredible microwork, executed with surgical precision. In an instant, the press strikes the circle with insane power, and the metal from fine grains turns into a pattern that thousands of people will see in their pockets and wallets. And it's not just one strike. Some machines have double-sided stamping, where both the obverse and reverse are applied at once. All in a fraction of a second. The speed is impressive. One machine shoots out 750 coins per minute, and dozens of such presses work simultaneously in the workshops, so tens of millions of coins are produced in a day. It's like music, only instead of drums, it strikes on metal, and instead of a melody, a chain of shine and power. After stamping, the coins don't shine right away. They are still warm, and may have small burrs. Next on the conveyor, the coins move to inspection machines. Laser sensors determine the exact diameter and thickness. Visual cameras search for defects in the relief and surface. The human hand is still necessary for rejecting flawed specimens. And so, the coin has passed through all the infernal stages, from the hot furnace to the press strike, and is now ready for its grand debut into the real world. But before that, a final march through the packaging area. Coins come off the conveyor, clinking, flashing, rustling. They are no longer counted individually. They are counted by weight. They are poured into special metal bags or large containers, similar to coffee bags, only each one holds up to 4,000 coins. For example, a standard bag of quarters is $1,000, and the weight of such a package is about 60 pounds. Impressive, right? When a bag is filled, it is hermetically sealed. A seal and a barcode are applied. Next, onto a pallet with hundreds of its brethren. All this into huge trucks that deliver money across the country. To banks, ATMs, stores, soda machines, the military, wherever. And sometimes they are packaged in rolls, small paper tubes. These are for retail circulation. They pour into boxes, clicking like casino chips, and you can already hear them clinking in someone's cash register. This is how an everyday miracle is born. You drop a coin into a parking meter, and behind it is a whole story from a hot workshop, fire, hydraulics, and people who give metal life. Every year, over 100 million cubic meters of plywood are produced worldwide. That's enough to cover every roof in the United States with a whole tree. But few people know how this journey actually begins. Imagine a wet log, still smelling of the forest, enters steaming chambers, passes through steam, knives, fire, and a pressure of 250 psi to become a wall, a roof, or even a stage. How is a log transformed into plywood that will last for decades? And what secret does the peeling process hide? If you watch until the end, you'll discover what they don't write in textbooks. The factory wakes up before dawn. With a deep roar, the gates open and trucks with freshly cut logs slowly drive onto the site. You should see them. Oaks, pines, poplars, true forest giants, long, thick, heavy, with wet bark and the aroma of a freshly felled forest. The wood is still breathing, still warm from the sun that shone on it for the last time. And so it begins. The logs are dumped onto a hydraulic feeder, where they move like logs in a mountain stream. Only instead of water, a system of rollers and chains is at work, and instead of a river, washing chambers, loud and ruthless. Bam! A jet of water under a pressure of 1000 psi, almost like a fire hose, hits the wood from all sides. All the mud, dust, and pieces of bark are torn off, like old skin. The logs spin, collide, foam, and hum. It looks as if the wood is undergoing a purification ritual before becoming something greater. After such a washing, they shine. But that's not enough. The wood is strong, rigid. You can't peel it like butter. So next, the steam chamber, a real wooden spa resort, but on an industrial scale. The logs drive onto an overhead crane, are lifted, and slowly submerged into giant cylinders, steam vats 60 feet long. And there, behind closed steel doors, begins what engineers call fiber softening, but I would call it wood stewing. Inside, it's 220 degrees Fahrenheit. The steam is thick, saturated. For 8 or even 12 hours, the logs soak in this environment. The steam penetrates to the core, the fibers relax, the resin starts to flow a little. And if you listen closely, it's as if you can hear the wood sigh, as if admitting, "Okay, I'm ready, make me into plywood, make me." They are taken out, and the logs are no longer the same. If at first they crackled with tension, now they are flexible, elastic like wet towels. Steam still billows from the bark, wood chips remain on the floor. The smell is like a sauna in the forest after a rain. They are stacked on roller conveyors and prepared for the next step, peeling, where they will lose their wooden identity, but acquire a new one. The log, fresh from the steam bath, is still smoking, as if someone just threw it from a pot onto the cold concrete. It is grabbed by a mechanical clamp, huge, like a transformer's paw, and lifted to the peeling machine, a giant with a steel mouth that is already humming, like a Harley-Davidson's engine at full throttle. This machine is a centrifugal peeling line, or simply put, a shredder. The log, heated and pliable, is mounted at the center of rotation, like a kebab on a skewer. It begins to spin slowly, then faster, even faster. And here the peeling knife comes into play, long, straight like a samurai sword, only made of steel and as wide as the entire log, 4 or 5 feet. And it doesn't cut. It peels, layer by layer, strip by strip. Screech! Shh! Vroom! The log spins, and a thin, flexible layer of wood comes off it, only 1/16 of an inch thick. It unfurls like a gift wrap ribbon, only instead of glitter, there's warmth, steam, and the smell of fresh wood. And instead of music, the roar of hydraulics and the rhythmic rustle of the plywood roll. This ribbon is veneer, the basis of plywood, its soul. It comes out without stopping, tens, sometimes hundreds of feet long, is rolled up or automatically cut into large sheets, typically 4 by 8 feet. Peeling is a sensitive process. The log must be straight, symmetrical, moist, but not too soft. If it cracks, it's over. The veneer will have holes or waves, and the plywood won't be grade A, but oh no. Operators carefully monitor every movement. On the display, graphs of speed, pressure, layer thickness, cameras capture every knot. If something goes wrong somewhere, the machine stops in a second. And then they fix it, readjust it, and back to the fight. When the log is exhausted to the core, what remains is a core, a few inches thick. It's automatically ejected to the side, to be later processed into sawdust, fuel, or wood chips. Nothing is wasted here. Everything will be used. And the veneer sheets, hot, pliable, still smelling of steam, race onto the dryer. But for a moment, as they come off the knife, they are incredible. This is living wood, which has already lost its tree form, but has not yet become plywood. It flows like water from a tree. It dances like a gymnast's ribbon. It rustles like paper, but carries the strength of a trunk. As soon as the veneer ribbons come off the knife, they are still damp, steaming, like leaves after a thunderstorm. And so, they are picked up by an automaton, pulled into a drying line, incredibly long, like a train in Texas. Inside, hot air, about 200 degrees Fahrenheit. Flows are accelerated by fans. The sheets race along a conveyor belt at a set speed. 10 or 15 minutes, and the veneer comes out dry as a bone. And at the same time, still flexible, because if you over-dry it, it will break like a chip. And if you under-dry it, the resin won't stick later. Everything, down to the micron, down to the second. It's not just automation at work here, but also the intuition of the dryer operator, who can tell by sound and smell. This oak is still damp. Next, sorting. Veneer sheets, dozens, hundreds, roll onto an inspection platform, where operators or modern cameras with artificial intelligence decide where each should go. A sheet without knots, perfectly even, goes for the face layer, the highest grade. With small cracks to the middle, with large defects into the inner layers, or for backing. Everything that doesn't fit is shredded and sent for recycling. Nothing goes to waste. The selected sheets are fed to glue applicators, huge drums that evenly roll on a waterproof phenol formaldehyde resin. It's dark brown, thick, sticky, smells sharp, like a school desk after woodshop class. And here, everything is important. The layer of glue, the temperature of the sheet, the direction of the fibers. Because plywood isn't just glued sheets, it's cross-laminated layers, where each layer runs perpendicular to the previous one. This is how it gets its mechanical strength, flexibility, and resistance to warping, like a bulletproof vest, but made of wood. The finished sandwiches of several layers are placed in a giant hydraulic press that applies pressure from 150 to 250 psi at a temperature of about 300 degrees Fahrenheit. Inside the press, it's hell, but a controlled one. 10 minutes and the resin hardens, binding the fibers into a single body. The plywood becomes monolithic, hard, sanded from the inside out. This moment is the culmination of the entire process. Here, from wood and glue, a plywood sheet is born, ready for battle. Coming out of the press, the sheet is still hot. It is laid on a cooling conveyor, a wind tunnel where cold air draws off the residual heat. Then, a sanding machine. On both sides, large rollers with sandpaper remove microns of irregularities, even out the surface, remove excess glue. Next, cutting into standard formats, usually 4 by 8 feet, although a customer can request 6 by 10 feet, or even mini sheets. Then, quality control, scanning, marking, packaging. Each sheet is marked with a code, a grade stamp, a production date. It is packed in stacks of 40 to 60 pieces, wrapped in stretch film, and off to the warehouses. Each sheet that leaves the factory has passed through water, steam, blades, fire, a press, and saws. And now it can be anything. It becomes a wall in a new house in Kansas, or the back of a chair in a New York coffee shop. Sometimes, the level of a stage in a music school in Iowa. Another time, the roof of a house in Mississippi, the floor of a trailer somewhere in the middle of Arizona, or even the body of a truck speeding down I-80 at night. And each time, thousands of layers of wood hold together, as if whispering, "We are plywood. We are stronger than we look." What made of plywood is right next to you right now?